Today we'll start our class. Before discussing the things for today's class, uh, let me just briefly tell us what we have done in the last class. So in the last class, we started our discussion from what is the difference between a isothermal process and adiabatic process. So basically, the slope is in the difference of the slope actually. So to draw isothermal, this is a isotherm, and this is how the curve of adiabatic process looks like. Okay. So for isothermal, this is a PV diagram. So this is the isothermal, and this is a adiabatic process. Okay. So for the isothermal case, the slope of the curve is dP by dV equal to minus P by V. And for case of adiabatic process, the curve is dP by dP equal to, there's a extra gamma factor is there, which is the adiabatic ratio, you can say, E by V. And also we have derived in our atmosphere, uh, the air cools from higher to from lower altitude to higher altitude through this adiabatic process actually. So so for that, how the temperature of the air changes basically with height. So that is basically known as the adiabatic lapse rate. Okay, in atmosphere. So the expression of that how the temperature changes with the height. So that expression is also derived. That is dT by dH is equal to minus gamma minus 1 by gamma into GL by R. Okay, it's known as the lapse rate in atmosphere. Okay. Next, we have also discussed about the cyclic process. Okay, cyclic process, from the name itself you already know. So it starts. So it's basically goes back to the position where it started. Okay, so this is how the PV diagram of a cyclic process looks like. Okay, so we discussed the properties of the cyclic process. So one of the properties, its internal energy, change in internal energy delta U, that should be equal to 0 for a cyclic process. So that means the work done is basically delta W is basically equal to delta Q. Okay. So the heat uh, input, Q input minus Q output will be basically the net work done for a cyclic process. Okay. So yeah. So then next we have also discussed about the heat engine. Uh, so heat we see, if you watch the PV diagram, or yeah, the PV diagram of a heat engine. So this that basically obeys the cyclic process actually. So this is the basic structure of a heat engine looks like. Okay. So heat engine. So it basically this is at hot reservoir T1, and this is the engine. It is doing the work T2. So it basically pulls energy from T1. So T1 is higher than T2, and Q1 Q2, and so it pulls, the engine pulls some energy from the hot reservoir, and then it's dumped into the cold reservoir, and during that process it does some work, so that denoted by W. Okay. This is the basic structure of any heat engine, the general structure. So the efficiency for this heat engine, for any kind of heat engine, the efficiency should be, this is the general formula, is W by Q1. Okay, so W is basically the work done, and Q1 is the heat input. Okay, for any general heat engine, this is the formula of the efficiency. So here it would be the work done is Q1 minus Q2 by Q1. Okay. Now for the case of ideal heat engine, so that means the Carnot engine, for the case of a Carnot engine, for Carnot engine, you can write the formula like this: eta equal to 1 minus T2 by T1. Okay. That is for a case of for the ideal case. Okay, if the engine is an ideal engine or a Carnot engine, in that case the efficiency would be 1 minus T2 by T1. This is the maximum efficiency that a heat engine can achieve. Okay. If it is basically operating between a temperature T2 and T1, in that case the highest efficiency that heat engine can achieve is basically this given by this formula. Okay, and this is the general formula. Okay, or you can write it like this also, uh, just for consistency: Q2 minus Q3. Yeah. And if you observe the processes, like the kind of processes that is happening inside the heat engine, so there are basically two types of processes. So in the PV diagram, it looks like this. Now, if you want to figure out like which curve denotes what type of process, you can easily do it by checking the slope actually. Okay. From the nature of the from the nature of this curve, you can easily predict it can be either isothermal or it can be adabatic. Okay. Now you can see these curves like if you name them A, B, C, D. Okay. This AB and this CD, AB and CD. Okay, so AB and CD has less steeper than AD and BC, right? So AB and CD are basically isothermal processes. Okay, isothermal process. If you look their slope, this AD and BC has higher slope compared to AB and CD, right? So AB and CD should be isothermal process here. And so the other two processes, that is AD and BC, is the diabatic process. Okay. So this is the basic structure of a heat engine. Okay. This is the PV diagram. This is the efficiency, and by doing the what is the work done during each of the process, if you calculate from the work done and heat input output, from there also you can prove this formula. Actually, okay, this formula of the heat engine. Okay, Carnot engine. Uh, Next we discuss about the refrigerator. Okay. Refrigerator. So what refrigerator does is actually, so this is how the refrigerator looks like. So this is T2, this is cold reservoir, this is T1 hot reservoir, so T2 is colder than T1. Now the refrigerator does the opposite what a heat engine is doing. So it basically pulls heat from the colder reservoir to the and dump it into the hotter reservoir. And since it's not spontaneous, right? So you cannot like spontaneously take heat from cold system and then dump it into a hot system, right? So for doing that, you have to do the work from the outside. So in the case of refrigerator, you have to put some work outside, external W. Okay. So this is how the any kind of refrigerator, like in our daily purpose, like the fridge, how the fridge and all is working. So it basically dump the heat from the colder part to hotter part. So that means the colder part will become much colder. Okay. So that the same principle is used by the AC or the what is called the fridge, everything. Okay. And in this case, instead of efficiency, so there is another parameter which is known as the coefficient of performance, COP. This the definition of COP is a bit different from the efficiency which we have discussed in the case of a heat engine. So the coefficient of performance is basically defined as Q2 by W. Okay. Q2 is heat that is taken from the cold reservoir and W is the work done. Okay. For a case of an Yeah. So in this case also the maximum COP this refrigerator can attain. So in this also you can write it like this: Q2 by Q1 minus Q2. So the maximum COP that the reservoir can attain is also T2 by T1 minus T2. Okay.
What is the full form of
And
COP, you said?
for case of an reservoir, the PV diagram will be same. What will be changed is the direction. Okay, so the direction you see for in the case of a refrigerator, the direction of this process of the in the PV diagram will be like this. Okay, the arrows will be changed. Okay. Next we discussed about the Carnot theory, and yeah, Carnot theory is we know that so is like Carnot theory.
What was the full form of COP that you said?
Yes, can you repeat?
I'm asking what is the full form of COP?
What is the full form of
COP.
COP? Full form is coefficient of performance. Okay, coefficient
Performance. Okay.
of performance. Yes, yes. So, Carnot's theorem is a very simple theory. Okay, so according to the Carnot's theorem, so it's like so Carnot engine has the maximum efficiency. So, like if there are two temperature, okay, like if a heat engine is operating between two temperature T1 and T2, okay, for the case the Carnot engine that has a efficiency we know eta equal to 1 minus T2 by T1. So this is the maximum efficiency that heat engine can attain. Okay, so this is basically the statement of Carnot's theory. Okay. Next is the Clausius theory. Okay. So the Clausius theory is saying is that uh, yeah, Clausius theory is that so according to the Clausius theory, uh, so if there are two cyclic processes happening in the heat engine, one is a reversible and one is a irreversible. Okay. Two cyclic process. Okay. In that case, for the case of the reversible one, if the efficiency for the reversible cycle is denoted by eta c and for the irreversible one it's denoted by eta e, in that case eta c will be always greater than eta e. Okay. So this is the statement of process theory. And next, from this theory, you can actually prove the Clausius inequality. Okay, so the Clausius inequality is given by this statement of Clausius inequality. So dq by t close integral equal to 0. So that this means during this any cyclic process, let's suppose this is a cyclic process, the dq by t, that means the overall change in heat during this whole process, since it's a closed integral, so that means during this whole process of starting to ending in the same point, the dq by dt, this quantity can be equal to 0 or it can be less than 0. Equal to 0 is for the case of reversible process and less than 0 is for the case of irreversible process. Okay, this is the statement of process inequality. Okay. And yeah, and also we have defined this dq by dt as entropy. Okay, uh, so dq by t defined as dq by t as delta s. Okay. Integration delta S from, let's suppose you will do from state 1 to state 2, some process, some path. This is denoted by delta S. So delta is, this is the entropy. Okay, we define it as entropy. So it is a state function. Okay, it's a state function. So it only depends upon the initial and final state. Okay, depends on initial and final state. Okay. And also we have discussed like the change in entropy for different processes, for isothermal process, for isochoric, isobaric. Okay, in case of a phase transition, in that case also latent is involved, right? So in the case of phase transition also, what is the formula of entropy? So those things also have discussed. Okay. So now so these are the pretty much things that we have discussed in the last class. Now for this class we will start from yeah. Yeah, so we'll start from the case of reversible heat engine and irreversible heat engine. So, so from Clausius statement, from Clausius theory, if there are two types of engine that is working, let's suppose from T1 to T2. Okay, these are two types of engine. Let's suppose so it pulls Q1, Q2, and does some work W. And here also it pulls, let's suppose Q1 and it done some work. So this is, let's suppose reversible engine, that is the Carnot engine basically, and let's suppose this is a irreversible engine. The any ideal engine, okay, that is in our like in our regular daily life, any engine is basically irreversible engine. No engine can be reversible, right? So let's suppose this is irreversible engine. In that case, let's suppose the work done is W prime and the heat that is going to the cold reservoir. Let's suppose take that heat as Q2 prime. So we know that for the case of irreversible engine, let's suppose the efficiency is eta I, and reversible engine eta I, and so reversible engine eta R, and irreversible engine eta I. So from Clausius theory, you already know eta I is always less than eta R, right? Eta for the reversible engine or the Carnot engine always has the maximum efficiency, right? So that means the work done should be smaller compared to the reversible one, right? So that means the Q2 prime will be higher than the Q2. Okay, so that means there would be some excess heat that is going towards the cold reservoir compared to the reversible engine. Okay, in the case of irreversible engine. Yeah. That means for the case of reversible engine, if you see the delta is reversible, so if you calculate the change in entropy for the case of reversible engine, the change in entropy for the system, inside the system, if you calculate the change in entropy, that is for the system, that is equal to 0, and delta S system is equal to 0, and delta S for the environment, that is the surroundings, that is also 0. So the change in entropy for the entire universe, that is delta S system plus delta S surroundings, okay, both are equal to 0. So for that, so the main takeaway home is that for case of a reversible engine, the change in entropy in the universe is equal to 0. So there is no change in entropy. Okay. So for the system as well as the surroundings, the change in entropy is equal to 0. But for the case of an irreversible engine, the delta is, we calculate the delta S universe is given by QE by T2. Okay. QE is basically the excess heat compared to the reversible engine. Okay. So this delta S universe is basically given by QE by T2. Okay. So that means it's always increasing. Okay. So this is greater than 0. So for a case of an irreversible engine, the change in entropy in the universe is always greater than 0. Okay. For the reversible engines, it is equal to 0. So the entropy principle is looks like this. Okay, so if you write a general entropic principle, if the equation looks like this: entropic principle delta S U is always greater than equal to 0. As you can see, so whatever process you do in our daily life in the universe, basically, whatever process is happening, it can so for that process either the change in entropy of the universe will equal to 0 or it can increase. Okay, it never decrease actually. Okay. So by increasing the entropy, the system basically wants to attain the equilibrium state. Okay. By increasing the entropy. Okay. So for the entropy of the universe is always either increasing or it is equal to 0 for any kind of process. Okay. Okay, now we'll discuss the change in entropy for some processes. Okay, so this is some important process. Okay, the first process is the free expansion. Okay. Change in entropy in free expansion. Okay. So whenever you see free expansion in any kind of problem, okay, you always know that during the free expansion, basically what happens, this is temperature, although the gas or whatever fluid is there, it basically expanding. Okay, so if it's a normal expansion, so you know that during the expansion the temperature change, right? But in case of a free expansion, the temperature doesn't change. Okay, so delta T is equal to 0 for free expansion. Okay, so no change in temperature. Okay. This is one property of free expansion. So that means the delta U is also equal to 0. Okay. So in this case, so you can easily calculate the change in entropy also. So you know dq equal to du plus pdv. So this equation, this is first law of thermodynamics. This law you can write it like this: tds equal to du plus pdv. Since du is equal to 0, so ds you can write p dv by t. P by t you can write as from ideal gas equation, you know PV equal to nRT, right? So from here you can write P by T as nRV by dV. If you do the integration, you will get delta S equal to nR ln V2 by V1. Okay. So this is the change in entropy for the case of an free expansion. Okay, so whenever in a problem, if it's mentioned that the system does some free expansion, there is some free expansion happening in the system, what is the change in entropy? So in that case, you can use this formula. Yeah. Next is for a general system. Okay. So let's suppose if there is some general process is happening, or general reversible process. Okay. General reverse, not any special case like isochoric or isobaric or adiabatic, not any special case. Any kind of reversible process is happening. In that case, what is the expression of? You can say a general expression of the change in entropy. So for that, we first have to write the equation that is TdS is equal to du plus pdv. Okay, we can write du as cv dt, right? So NCVDT. Let's suppose n mole of n mole of gas or any kind of system is there. So NCVDT plus PdV. Now we can, so we want to calculate the change in entropy. So dA is equal to NCV dt by T plus P E dV by T. So similar way, P by T you can write from ideal gas equation, P by T equal to N NR by V, right? So you can substitute this thing here. If you do the substitution, ds S1 to S2, if you do the integration, NCV T1 to T2 dt by T and NR by dV by V, integration V1 to V2. If you do all this integration, you get delta S as NCV ln T2 by T1 plus NR ln V2 by V1. Yeah. Now you can also write in other way also. You can basically you can write in terms of Cp also. You know, Cp minus Cv equal to R for the case of an ideal gas. Okay. So from that you can use that also. From by using this equation you can write this formula in terms of Cp also. Similar way, you can write V2 by V1 as since P equal to, so you can write as V2 by V1 as V1 by T2 by P2 by T1, right? So in that, by substituting this here also you can write this equation in terms of P1, P and T, pressure and temperature also. Okay, so depending upon the problem, whatever way you can write this the form of this delta S, this general form delta S. Okay. So this is one important expression to remember actually. So this process you can if you remember this particular expression. So from this expression you can also write what is the change in entropy for a special case. Okay, let's suppose the system is isobaric or it's a adiabatic process. So the temperature, the dq will equal to 0. For a isothermal process, the temperature will be equal, it's no change in temperature. So this term will become basically equal to 0. So for any special case also you can basically rewrite this expression, right? So okay. So next is the yeah. Okay, so next we'll discuss some process where we'll discuss how this what is the basically significance of entropy, like how during different types of process how the entropy is changing, how the entropy of the system, how the entropy of surroundings, the entropy of total universe, how both all of these things are changing. So we'll look at that by an example. Okay, so first we take the example of the diffusion of gas. Okay, so we know that let's suppose there is a gas mixture, not a gas mixture, so the two gases are separated by a wall. Let's suppose this is a separation. So in, let's suppose this right left hand part has N1 mole of gas and right hand part has N2 mole of gas. Uh, let's suppose the temperature and pressure is given by P and T. Okay. P and T before the mixing. Okay. Now you remove this partition, and after that the both the gas got mixed. Okay, you remove the partition, and both the gas got mixed. Okay. So in that case, we know that from the concept of partial pressure is that the N1 mole of the N1 mole of type 1 gas has pressure P1 equal to N1 by N1 plus N2 by P into P, and type 2 gas uh, the the partial pressure P2 is for type 2 gas is N2 by N1 plus N2 by P. So that means this is the initial state. The initial state, let's suppose the entropy is this right hand side, this type 1 gas has entropy S1, and left hand side the gas type 2 gas has entropy S2. And after the mixing, let's suppose the total entropy become S. Okay. Now for this case, the initial case, so that means during the mixing there is some change in entropy. So initially the initial entropy is S1 plus S2 before the mixing, and after the mixing the final entropy is final become S, right? So that means the change in entropy delta is equal to S final minus S initial, right? Since it's like entropy units a state function, so it's only depend upon the initial and final state. Okay. So S final is S minus S1 plus S2, right? So in that case, so if you calculate the final entropy S, so in the case of final entropy, just use if you use this formula, okay, so we know the change in entropy, the general form of change in entropy. So if you use this formula here, we'll be getting this delta S as, if you do all the calculation, you will get N1 R ln P by P1 y plus N2 R ln P by P2. Okay. After doing all the calculations, so you can calculate the entropy for the final process, you calculate the entropy for the initial process, this left hand side and the right hand side. Do the calculation and substitute it here. You will be getting delta S as N1R ln P by P1 and N2R ln P by P2. Now you know this expression of P1 by P2 in terms of P, right? This form of expression you already know. You can substitute this thing here. So after doing the substitution, you will be getting delta S as, so delta S will take the form like this, N1R ln N1 plus N2 by N1 plus N2R ln N1 plus N2 by N2. Okay. So you can write it in for let's suppose there are instead of two types of gas, let's suppose n numbers of gas is there, n types of gas is there. So you are basically mixing n type of gas instead of two types of gas. Okay. So for that case, the general change of entropy for this kind of a system, for a case of mixing, the delta S is equal to I, the summation, let's write in terms of summation, I Ni R ln summation over I Ni by Ni. So I is run from, let's suppose 1 to n. Okay, 1 to n. So if n equal to 2, then it will take this specific form. If n equal to 3, there will be another term will be there, n1 plus n2 plus n3, right? This is a general form. Okay, this is the general form of you can say change in entropy due to mixing. Okay, due to mixing, or you can say entropy of mixing, something like that. So this is a general format. So you know, so whenever so this process, so this is also because of diffusion. This mixing is also happening because of diffusion, right? So diffusion. Now in this case, so this Ni by this summation of Ni by Ni, you know already it will be greater than 1, right? So in this case, this thing is always greater than 1. Okay. So greater than 1, this ensures that this expression will be equal greater than equal to 0. So delta is also will be greater than equal to 0. Delta is will be always greater than equal to 0. Okay. Okay. So that means during this process, the entropy of the system is increasing, right? So that means the entropy of the universe is also increasing. Okay. Yeah. So now, so now we'll write some physical interpretation, like physical properties of entropy. Okay. So, uh, from the entire study that we have done, from that study we can basically conclude what are the basic properties of entropy. Okay. So, properties of entropy. Okay. Uh, so as we discussed, during so as we discussed initially from process theory, also we have discussed is that for any irreversible process, we know the entropy of the system or the entropy of the universe, you can say, is always increasing. Okay. For any irreversible process or any kind of natural process. So one another way also you can interpret it like this: the during all of this process, the randomness inside the system is also increasing. So this entropy can be always connected with the randomness of the system. During this gas mixture, also you can see initially this gas is basically confined inside a volume. Like this type 1 gas is confined into this volume, and type 2 gas is confined into into this particular volume. Okay. Now when you mix this confined volume is also getting increased. So now each of the gas particle can basically access more volume compared to the initial state, right? So in that case, it means that the randomness of the gas particles also get increased. So that is one of the results. So that is one of the reason why the entropy is also get increased, right? So we can also connect the randomness of the system to the entropy of the system also. So you can write it like this. So property 1. So entropy entropy increases in during or irreversible or natural processes. Second is the randomness in a system also measures entropy. So there is a formula for that actually. So if you study statistical mechanics in the further courses basically, so from that course actually has a very good application of this particular formula. Okay, that formula is given by is equal to kb log w. So this w is basically is the you can say the number of microstates.
Number
Okay,
of mic-
yeah.
W is the number of microstates, right? That's what they were saying.
Yeah, can you say again?
Yeah, I was just saying that W is the number of microstates you said, right?
Yeah, yeah, yeah. It's the number of microstates. Yeah. So,
Mm-hmm.
number of microstates, accessible microstates for the system. Number of accessible microstates. So, in a simple way, is that when you mix the gas basically here, for each of the gas particles, the number of microstates that each of these gas particles can attain becomes higher. Okay. So for that reason, the W also become higher. So the change in entropy is also become higher. Okay. So so this things is actually discussed in a greater detail in the course of statistical mechanics. So if you, for any kind of system, if you can calculate the number of microstate that the system can access basically, from that number you can calculate what is the entropy of the system. So that number, the number of microstates gives you a measure of the randomness of the system. Okay. For a gas system like this, for a very small particle system, this number will be enormous number, right? That is there. But since but since it can be done, okay. Although the number will be very high, but since although it can be calculated, okay. Using some statistical techniques. So there is another example also you can see. So in this case, like crystallization, okay. Now, in the case of crystallization, what happens? The particles the atoms, it's like they kind of arrange themselves in a very ordered structure. Okay. So from that perspective, it might looks like that the system attains a order state. So randomization inside the system get decreased. Okay. So it might looks like the entropy of the system got decreased. But what happens that although the entropy of the system got decreased here, but during this process, this exchanges some heat into the surroundings. Okay, so it basically exerts some heat into the surroundings. So if you calculate the total change in entropy, that is the delta S universe, that is related to delta S system and delta S surroundings. If you look that, the delta S universe is always will be greater than 0. Okay. Although in this case, the particles in crystallization process, you know, in the crystal structure, every particles are in an order structure. Okay. So that means the randomization inside the system got decreased. Okay. So that means the change in entropy for the case of system is less than 0. But for the surroundings, since there is some heat that is coming out into the system, for the so the change in entropy in the surroundings is greater than 0, and this surrounding change should be greater than the change in the system. Okay. To ensure that the universe, the change in entropy in the universe would always be greater than 0. So this is also a process. This is also a very important thing in the field of statistical mechanics, like in the field of you can say material science also. Okay, where this spontaneously this crystallization process is happening to basically to reach the system in equilibrium. Okay. By doing that, the change in entropy of the universe is basically increasing. So in that way, you can say the system is basically reaching towards the equilibrium. Okay. So this is some basic properties of entropy. Okay. Now next, now we'll discuss about the TS diagram. Okay. So so previously whatever process and the thermodynamic like diagram like to basically discuss what is the property of the process, we basically describe that thing in terms of PV diagram, right? Now instead of using P and V as a thermodynamic coordinate, we can also use temperature and entropy. Okay, since the PV P multiplied by V gives you the unit of energy. Similarly, the multiplication of T and S also gives you the unit of energy. Okay, so instead of using P and V as a thermodynamic coordinate, you can also use the T and S also as a thermodynamic coordinate. Okay. Now, if you use T and S as a thermodynamic coordinate, uh, the the structure, if you basically do a coordinate transformation from P to V to T to S, the structure of that PV diagram to TS diagram will also get changed. Okay, obviously. So there is a way to remember it. Okay. So since you are changing, so the way we have calculated, like for the PV diagram, you know, for adiabatic or isothermal process, we calculate their slope, right? In order to remember how the curve basically for a isothermal process or for an adiabatic process, how the curves looks like. In order to interpret that, we use the slope of the curve, right? Now, for the case of a TS diagram, also you'll do the same. Okay, so we'll start from the isobaric process. Okay, isobaric process. So we know the how temperature and a change in entropy is related with each other. So it's like TdS. So you know dq equal to du, right? For the case of an isobaric process, we know dv is equal to 0. So from what is it called? From the case of yeah, for the case of from the first law of thermodynamics, you can write um, dq equal to du plus dw. So dv is equal to 0 for sorry, this is isochloric, not isobaric. One second. Yeah, it is isochloric. Yeah. dv equal to 0, so dw will be equal to 0. So you can write yeah. So from here you can write dq as du. So dq you can write as tds equal to cv dt. So from here you can write the slope as ds dt equal to t by cv. Okay. Similarly, for case of an isobaric process, for in a TS diagram, the slope is ds by dt equal to t by cv. Okay. For isothermal process,
DSDT should be CV by T, right?
yeah, cv by t. Yeah. So ds dt will be cv. Yeah. ds by dt equal to cv by ts. cp by t. Yeah. For the case of isothermal process, ds by dt equal to 0. Sorry, dt by ds also you can say whatever rule. ds by dt or dt by ds equal to 0. And it's better to write in terms of dt by ds. Okay. Since dt will be the p coordinate, so it's sorry, the y coordinate. So it would be better to write in terms of dt by ds. So dt by ds would be t by cv, dt by ds would be uh, t by cp. For isothermal process, dt by ds would be 0. This is a constant volume, this is a constant pressure, this is a constant temperature. And for adiabatic process, dt by ds, adiabatic process, that means the heat is fixed. dt by ds equal to infinite. Okay. So if you draw it, it looks like this. Okay. This. So if Cp is greater than Cv, in that case, for case of an so for the isochoric process has a higher slope compared to the isobaric process. Cp is greater than Cv, right? So if you draw it in a TS diagram, all these kinds of curves, isobaric and adiabatic. So it will looks like this. Adiabatic has an infinite slope, so it will be a straight line along the t-axis. Okay, so this is the adiabatic. For the case of isochoric, it looks like this, and isobaric, it looks like this. So isochoric has a higher slope, isobaric has a lower slope, and for isothermal, it will look like this, a straight line, since it has a slope of 0. Okay. So this is how a basic TS diagram looks like compared to a diabetic PV diagram. Okay. So PV diagram, it looks like this. So PV diagram, if you compare it like this, so PV diagram, isochoric process looks like this, a straight line along P. This is isochoric. Isobaric looks like this, isobaric. adiabatic process looks like this, and isothermal process looks like this. Okay. This is isothermal, this is adiabatic. Okay. So as you can see, there is clear distinction between TS diagram and PV diagram between each of these processes. Okay. Okay. So that means in a problem, if instead of giving PV diagram, if TS diagram is given, so from the structure of the diagram you can easily identify which of the processes are happening into the system. Okay, so now let's construct the diagram for heat engine from the PV diagram to the TS diagram. Okay, so in the PV diagram we know for the case of heat engine it looks like this. So it's isothermal, adiabatic. So that's 1, 2, 3, 4. For the case of heat engine, the cyclic process flows this clockwise direction. Okay, this is for heat engine. So these are the adiabats. These are the 1, 2, 4 and 2, 2, 3 are adiabatics, and 1, 2, 2 and 4, 2, 3 are isothermal. Okay. This is for an heat engine. Now if you convert it into a TS diagram from PV diagram, it's very simple. So TS diagram, so uh, you can basically draw the isotherms. So these are isotherms. You can draw it as a straight line along this axis. So these will be the two isotherms. And adiabats, you know, these two adiabats. So these are the isotherms 1 to 2, 4 to 3, right? These are the isotherms. And the adiabats will be the straight line along the t-axis, right? So this will be the adiabats 1 to 4 and 2 to 3. Okay, so it's just a kind of a rectangular kind of a shape. Okay. And for the case of TS diagram also you can calculate the eta for a Carnot engine. So eta will take the similar form 1 minus T hot by T cold. You can prove the same if you the formula of efficiency by using this TS diagram also. Okay. The way we have done for the PV diagram, similar we can done for the TS diagram. So one more thing to remember. So in case of a TS diagram, if you want to calculate the okay, so if you want to calculate what is the heat input and what is the work done for the system, it can be easily calculated. So for case of an what do you call this cyclic process or this Carnot engine, the case of TS diagram, the area that is covered by this highest temperature TH, that area, this whole area is basically gives you the Q input, the heat input. Okay. And the area that is inside the curve during the cyclic process, this all these things only applicable for a cyclic process. Okay. So this area under the curve basically gives you the work done. Okay. So for any kind of process, if it's mentioned, okay, like if let's suppose the process looks like this, okay, this is how the process looks like. So in this case, if you are supposed to calculate what is the, let's suppose the uh, efficiency of this cycle. So in order to calculate the efficiency, you have to calculate the work done, right? So work done and heat input, okay, right? So So work done is basically sorry, the efficiency, if you want to calculate the efficiency basically, so efficiency is basically work done by heat input, right? So that means heat, in order to calculate the heat input, you have to calculate the area under this curve. Let's suppose this is the highest temperature TH. Okay, this is the area under this curve. Will give you the Q input, and the area that is closed by this curve is basically gives you the work done. Okay, so this gives you the work done, this area, and this input area gives you this whole area gives you the heat input. Okay, so in this way you can solve any kind of problem. Okay, if the problem is given in a TS diagram, or if the problem is given in the PV diagram also, you can convert that problem into the TS diagram. In that way also you can solve it. Okay. Yeah. We will solve some problem with that also. Now, next is some two important things. Okay, so uh, the basic principle of an internal combustion engine. Okay, IC engine you can say. So the engine that is used by the modern cars, the diesel engine and the petrol engine. Okay, so both two types of engine are basically known as the internal combustion engine. Okay, so depending upon what is the type of fuel that is used in the engine, it can be a diesel engine, it can be a petrol engine. The mechanism of the engine is a bit slightly different. Okay, for the case of diesel and for the case of petrol engine. That is the reason we cannot basically give petrol to a diesel engine. Okay, so the engine basically doesn't work if you do that. Okay, for the case of a diesel engine, okay, sorry, for the case of a petrol engine, the kind of cycle that is happening to the petrol engine is known as a Otto cycle. Okay, Otto cycle you can say. Uh, the basic mechanism, I guess you know already. So, so the basic principle of IC engine. First is the Otto cycle. This Otto cycle is basically used in mostly the diesel petrol engine. So petrol engine is mostly used in, you know, the small cars like sedan cars. So they use these petrol engines. Okay, where you need you can say high RPM. Okay, like in bikes or small motor cars, they use these petrol engines. But for like heavy duty vehicles like lorry or these trucks, so these vehicles, heavy duty vehicles, basically use the diesel engine. Okay, so there in that for the case of diesel engine, the mechanism a bit different compared to the petrol engine. Okay, so so this Otto cycle, so Otto cycle, so how it's basically the basic working principle is like this. So there is a input valve, there is a output valve. Okay, there is a piston here. So what happens? This spark plug is also here. Okay, so what happens is there. So first, what happens is there is four strokes are there. So that's why this modern engine they call this as four-stroke engine. Okay, so there are four types of strokes are happening into the system. First is the intake stroke. So what happens is that the air comes, air and the mixture of air and fuel. That in this case it would be petrol. So air and fuel comes into the systems that known as the intake stroke. Okay, so first happening is the intake stroke. So it comes here. So the next what happens is the compression stroke. Okay, so compression stroke is that. So basically this piston moves upside. So because of that, the air pressure increases, right? The compression is happening. Okay. So because of the compression is happening, and this exhaust valve is also closed. So the pressure inside the gas is also increasing. So because of that, the temperature inside the gas fuel mixture is also increasing. So this is known as the compression stroke. Okay, compression stroke. Third step is the combustion. So combustion happen is that. So when the piston moves, let's suppose after a particular distance, let's suppose this distance. After that, what happens? This gas, the temperature of this gas fuel mixture becomes very high. After that, there's some sparks happen into this gas mixture, and because of the spark, there's a combustion happening in this gas and fuel mixture, and because of that, this internal combustion. So this combustion happens. So this is the combustion steps, and because of the combustion, there is some power that is exerted towards this piston, and the piston moves basically downwards. Okay, so this is known as the power stroke. This happens because of the sparking in the hot mixture of air and fuel. Okay, this is known as the power stroke. Okay. Next, after that, so when the piston moves downwards because of the power stroke, this exhaust valve opens. So this is the exhaust. The fifth steps, the exhaust valve open. So, and after that, the exhaust, this burnt air and fuel comes from the exhaust pipe. Okay, so this is known as the exhaust stroke. Okay. So this whole process is happen again and again, and because of that, this you can, if you see any kind of internal combustion engine, you will see these pistons always moving like top and bottom. So this kind of phenomena is happening. So this whole six process is happening because of in the system. So because of that, these pistons are moving in the engine. Okay. So during all of these processes, so different all of this intake stroke, compression stroke, power stroke, exhaust stroke. During all of these processes, so different processes are involved during this during this system, during this operation. So during the intake stroke, what happens is that so intake stroke is that this intake stroke is basically isobaric. Okay. These things you have to remember. During this intake stroke, when the pressure is when the air and fuel mixture is coming into this chamber, this is the isobaric process. Next is the combustion stroke. So during the combustion stroke, the compression stroke, the process 2. During the compression stroke, when basically this piston compressing this air and fuel mixture, during that process is basically the adiabatic process. Okay, adiabatic. Next is the combustion stroke is isochloric stroke, isochloric process. Okay, so this is the isochloric. The power stroke is adiabatic again, adiabatic. The exhaust stroke is again isochloric, and the exhaust output, that is the exhaust stroke, is the isobaric. Okay. So these are the like different types of process that is associated with all of these operations. Okay. Now if you for this case if you draw the Otto cycle in a PV diagram, it looks like this. Okay. This is whole diagram looks like. This is how it looks like. This is step 1, 2, 3, 4, step 5. So from 5 to 1, this is the intake stroke. Here is happening. From 1 to 2, it's the compression stroke. This is the adiabatic process. So this is the adiabatic process. So let me write it. This is the adiabatic. This is the isobaric. During this process 2 to 3, combustion is happening. So the heat is basically coming inside because of the sparking you can see, so heat is coming inside. So this stroke is the isochoric process. This is again adiabatic. This is isochoric. This is again isochoric. This is the exhaust. This is the 3 to 4. This is the power stroke. This is 3 to 4 and 4 to 1. This is again exhaust strokes. No, sorry, not exhaust stroke. This is exhaust. The piston comes down. So this is known as the isochoric. And lastly, the exhaust stroke. Okay, so 1 to 5. Okay, 1 to 5. So this is known as the exhaust stroke. Or this is the isobaric. Okay. Isobaric. This is the whole Otto cycle. This is the whole Otto cycle looks like. So during this exhaust, this isochoric process, the heat basically goes outside the system. Okay, so that's why during this process, this QC is the heat output of the system. QH is the heat input. Okay. This is how PV diagram it looks like. Similarly, you can draw this thing for case of an in a TS diagram also. Okay. Now, so for this Otto cycle, if you can also write its efficiency. Okay, so efficiency of the Otto cycle looks like this. So eta is equal to 1 minus V2 by V1 by gamma minus 1. So V2 is V2 by V1. So V1 by V2. So V1 by V2 is the known as the compression ratio. Okay. Compression ratio. Okay. Compression ratio means V1 is basically this volume of this chamber. Okay. So initially the chamber has volume V1. Okay. Initial volume. Now when the piston moves upwards, then this compression is happening. So the volume of the chamber reduced to V2. Okay. The final volume. So that compression ratio basically denoted by V1 by V2 R, and that ratio basically dictates how the efficiency of this engine looks like. Okay, like becomes. So this compression ratio decides what would be the efficiency of the engine. Okay. So you can write eta equal to 1 minus 1 by R gamma minus 1. So gamma is the adiabatic ratio. Okay. Okay, so this is the Otto cycle. Next is the diesel cycle. Okay. There is a difference between the Otto cycle and diesel cycle. There's a difference in the basic mechanism. Okay. So diesel cycle. Now, so if you see the diesel cycle, what happens that if you look at the piston engine, similar things here also there is a piston, there is a chamber, the input and there is an output. So instead of a spark, here there is a fuel injector is there. Okay. So this is the intake valve, this is the exhaust valve, and this is the fuel injector. Okay, this fuel injector. So in case of Otto cycle, what happened is that both air and fuel mixture comes from this intake valve. Okay. But in case of a diesel cycle, what happens? Initially the air comes. After the air comes, the compression happens, and when the air becomes hotter, after that the fuel inject into the gas. Okay. So instead of the air fuel mixture coming initially in the case of an Otto cycle, in the diesel cycle what happens? The fuel is injecting into the gas when it becomes hotter. Okay. This is the one of the difference in case of a diesel cycle compared to the petrol cycle. So here also the strokes are similar. Okay, so intake strokes, intake stroke. Next is the compression. Third is the combustion. Fourth is the power stroke. Fifth is the exhaust. And sixth is the exhaust stroke. Okay. All of the operations are quite similar with the Otto cycle, but there is this is one difference into the basic working principle. Okay, and because of that, if you watch its PV diagram, okay, this process of what 2 to 3, where this combustion is happening. In the case of an Otto cycle, this 2 to 3, this is combustion process. This combustion process, for the case of Otto cycle, it was an isochoric process. Okay, but for the case of a diesel cycle, this conversion process is basically an isobaric process. Okay, isobaric. This is our basic difference between a diesel cycle and a Otto cycle. Okay, so for the case of Otto cycle, it was an isochoric process. For a diesel cycle, it was an isobaric process, and because of that, if you draw its PV diagram, it will looks like this. Okay, 5 so here there is the difference here. It's this kind of a shape. Okay. It's Q going out, heat going out, heat going in. Okay, so as you can see, compared to the for a Otto cycle, as you can see here, it's an isochoric process, but here it's an isobaric process. Okay. So this is a difference between an isobaric and isochoric. Difference between Otto cycle and diesel cycle. And for this difference, the expression of efficiency also got changed. Okay, so if you calculate this efficiency eta, so eta will take a form like this: eta equal to 1 by gamma 1 minus in the denominator Vg by V2 by Vg by V2 by into V1 by V2 minus V1 by V2. This is gamma minus 1. This is also gamma minus 1. Okay. So here you can write compression ratio R as V1 by V2, and you also define another ratio, that is the fuel cutoff ratio. You can denote as rho, that we defined as V3 by V2. Okay. There are two ratios involved here. So one is the compression ratio, that is there also in case of an Otto cycle, and there is a new thing, that is rho, that is Vg by d2, that is known as the fuel cutoff ratio. Okay, so if you write the eta in terms of R and rho, so in that case eta will take a form like this: eta equal to 1 minus 1 by R gamma minus 1 by rho gamma minus 1 into gamma minus 1 of omega. So this is the final form of it. Okay, so this is the efficiency for case of a diesel cycle, and this is the efficiency. This is the efficiency for the case of an Otto cycle. Okay. So now, so after discussing it, we'll be solving some of the problems. Okay. So the problem number 1 is calculate the change in entropy when 10 gram of ice at minus 10 degree centigrade converted at 100 degree centigrade steam. Okay, so everything is given. Specific heat of ice is 2.1 kilojoule per kg per Kelvin. Latent heat of ice is also given, 33.6 kilojoule per kg. Latent heat of steam is also given, 2268 kilojoule per kg. And lastly, the specific heat of water. Okay. Since it involves, this problem involves phase transition, so you know all this latent heat and specific heat. Okay. Specific heat of water is given as 4.2 kilojoule per kg per Kelvin. So you already know. So there is 4 types of processes. Okay. So delta S, we know the basic form of delta S. So there are first there are 4 types of processes happening. First, what happens? Ice is minus 10 degree. So ice is minus 10 degree. It will, from minus 10 degree, it will first move to 0 degree, right? Minus 10 degree to 0 degree. So during that process, there will be change in entropy delta S1. Now from 0 degree ice, it will become 0 degree water, right? 0 degree water. So during that, there will be some change in entropy delta S2. Now from there, it will again become water, 0 degree water to 100 degree water, right? 100 degree centigrade water. So for that, there will be some change in entropy delta S3. And from 100 degree water, it will become 100 degree steam. So there is again phase transition is happening. So 100 degree centigrade steam. So again, there is some change in entropy will be there. Now for each of the change, so for delta S1, for the change in temperature, we know that entropy is basically given by this MC ln T2 by T1. For the case of phase transition, we know the change in entropy is basically mL by T. L is the latent heat during the phase transition. Again, the change for change in temperature, MC ln T2 by T1. And again, this phase transition, so mL by T. Okay. So total delta S would be delta S1 plus delta S2 plus delta S3 plus delta S4. So if you substitute all of the things, so first would be change in temperature 0.01. C is the specific 2100 for ice. Ln 273 to 263. Yeah. From minus 10 degree, it's become 0 degree, right? Delta S2, that is the phase transition, so mL. So we write everything in joule and gram, right? So it's 10 gram, right? So 10 gram. Okay. So joule and gram. Okay. So joule and gram, and its L is given in terms of kg. So we have to convert gram into kg. So 10 gram in kg would be 0.01 into kilojoule is 336000 by 273. Plus similarly here also specific M is 0.01. Specific heat of water is 4200 joule into ln of 373 by 273, plus again phase transition, that is 0.01 into 26000 373. So these are all the processes. You do the calculation getting delta as 87 joule per Kelvin. Okay, so first the best thing is that first write all of the processes that is happening. Temperature change, where the temperature change is happening, where the phase transition happening, and depending upon all the processes, write down its corresponding change in entropy. Okay. By doing that, you can easily calculate what is the total change of entropy for this type of systems. Okay. Yeah. So next problem is a problem that involves TS diagram actually. So problem 2. So there are basically two diagrams are given. Okay, so let me first draw the diagram. So TS diagram. So this is one TS diagram. TS. So first diagram looks like this. So it's a triangle. Okay. So the process moves like this. A, B, C. So it moves like this. Okay. This is T1. This is T2. This is S1. This is S2. Okay. And there's another one process, two process. For this process, the TS diagram looks like this. Flip triangle compared to the first process. So here it is T2, it is T1, this is S1, this is S2. Here the process moves like this, A, B, C. So it moves like this. Okay. Now the question is, calculate eta 1 by eta 2. Eta 1 is the efficient efficiency of cycle 1 and eta 2 is efficiency of cycle 2. Okay. So how do you calculate? So you know, so efficiency 1, so eta 1 you know, for any kind of processes, the general formula of calculating the efficiency of any kind of general cyclic process we know is eta is basically W, that is the work done by Q input, right? Heat input. And for the first process, you can see, okay, so for the first process, the heat input is basically, what is the heat input? That is the region that is covered by this AV curve, right? So that is basically this trapezium, you can say. So the area of this trapezium, this this A, B, S, S2, S1, this whole trapezium, right, is basically gives you the heat input. So Q input here is the area under the curve AB, right? Area under AB. So area under AB is basically the this area under the trapezium. Say this area under the trapezium area would be T1 plus T2 by 2 S1 minus S2, right? S1 minus S2 is this thing. T1, T2 is what is T1, T2? This by this, this plus this by 2, right? This is T1 by T2. And S1 and S1 minus S2 gives you this height of this trapezium. So area under the trapezium would be, or the Q input would be this one. And similarly, the work done would be, what is the work done? Work done would be the area under this curve ABC, right? So area under ABC. That is basically the this thing, right? Area under ABC and this thing. So that is basically the area under this triangle. So area under the triangle you already know, half into base into height. So that would be half into T2 minus T1. Here T2 minus T1 is basically, you can take it as height, T2 minus T1 into base, S2 minus S1, right? So eta will get as W by Q is basically would be, say, S1 minus S2, S2 minus S1 will cancel. So T1, T2 minus T1 by T2 plus T1, right? So this would be the eta 1 for the case of first cycle. Okay, okay. For the case of similarly for the case of second cycle also, the Q input. So here let's denote it at Q. Let's see Q input 1 and W1. Here it's Q input 2. So here Q input 2. What is the Q input 2? Area under the curve AB, right? Yeah. Yes. Mhm. Area under the curve AB, right? So that would be, yes. So this would be the heat input. Sorry. So this would be the heat input. Okay. So Q2 input would be T2 into S2 minus S1. Right. So this is basically this area of under this triangle, right? Now Q input is this. Now is the work done. That is the area under area of this ABC area under ABC. That is the triangle. So that would be half into T2 minus T1 by into S2 minus S1, right? That is the work done. So eta 2 would be similarly W by Q2 input. That gives you T2 minus T1 by 2 T2. Okay. Now if we do eta 2 by eta 1, it will give you 2 T2 by T1 plus T2. This is the ratio of the cycle. Okay. Okay, so you got it how it's coming basically. So the simple way is that so area under the curve which has the highest temperature, that would give you the heat input, and the total area covered by the cycle basically gives you the total work done. So if you take the ratio of both of them, you will get the efficiency. Okay. Okay. So this is one problem regarding that. The next problem is question 3. Find the entropy increment of an aluminum bar of mass 3 kg, okay, on heating it from 300 Kelvin to 600 Kelvin. Okay. If in this temperature interval specific, okay. So in this case, the specific heat of the aluminum is not fixed. Okay. So during this process, the heat capacity of aluminum varies. It varies like this. This expression is equal to A plus BT. So the specific heat of heat capacity of aluminum varies with temperature linearly. Okay, so where A is equal to 0.77 joule per gram Kelvin and B equal to 0.46 millijoule per gram Kelvin square. Okay. Basically, you increase, so the change in, you have to calculate the change in input. So options are also given. So option A is 1.063, option B is 2.015, option C is 0.152, and option D is 0.184 the kilojoule per Kelvin. So, so since only temperature is changing during this process, so you can use this formula dq equal to du. So TdS equal to Cv. Uh, it's not mentioned what it's happening, I guess, for constant volume. So Cv dt, right? Cv dt, yeah. So ds would be Cv dt by t. So if you do the integration, so delta S would be Cv ln uh, yeah. So here, so when you do the integration, it will be not simpler like this. So Cv is also dependent upon the temperature. So integration also includes the Cv, right? So it will write like this: integration T initial to T final. So A plus B into T into dt by T. Okay. To do it, it will give you. There is also M is there, so MCBD. M is there also in the formula. So first term gives you A into ln. So first integration gives you dt by t. Second integration gives you just dt. Okay. So M into A ln Tf by Ti plus B into Tf minus Ti, right? So if you do it, so the mass of the is 3 kg, okay. 3 kg. The other things are mentioned, everything is mentioned in okay. Yeah. Hmm. So it's better to write in terms of grams since the other units are given in terms of grams. So 3 kg you can write 3000 gram, right? Now, so A is 0.77, so 0.77 into ln T final by T initial, so 600 by 300 plus B into 600 minus 300. If you do the calculation, you're getting the delta S as 2.015 into 10 to the power 3 joule per Kelvin. Okay. This would be the correct answer. Kilojoule, if you convert it into kilojoule. Okay. Next is problem 4. This is a different type of problem. Okay. Problem 4. The internal energy of a system is given by the internal energy expression is U equal to A P square V. Okay. E is a positive constant, equal to positive constant. Okay. Find the equation of adiabats in PV plane. Find the equation of adiabats in PV plane. Okay. The equations, the options in the equations is given as an option. So AP plus 1 whole square equal to constant. Option B is B square AP plus 1 whole square equal to constant. C is B by AP square plus 1 equal to constant. And option D is B into AP plus 1 whole square equal to constant. Okay. Now the general trick to solve this kind of problem is that you have to start from the first law of thermodynamics, from the equational form of the first law of thermodynamics, that is dq equal to du plus dw. Okay, because this second law of thermodynamics is applicable for any kind of general system. Okay, so by substituting the necessary things, you can basically get the equation of the system. Okay, of the particular system that you are dealing with. So for this case, if you read the question carefully, it is mentioned you have to find the equation for the adiabat. Since it's mentioned adiabat, that means dq equal to 0. You have to put into this equation. You have to consider into this equation. Since it's adiabat, okay. So dq equal to 0. So we left with du equal to minus dw. Okay. Now for du, the expression is given u equal to, what is the u equal to a p square v. So d equal so a p square v. So du equal to minus dw, right? So du equal to a p square v and dw is p dv. Okay, and if you do the total derivative on the left hand side, so it will give you 2p dp av, sorry, ab into 2p dp plus, you can write it as a p square dv equal to minus p dv. Okay, and write this total derivative like this. Now if you collect the terms with dp and dv in right hand side and left hand side, you will be getting the expression like this: dv by v plus 2a by ap plus 1 dp. If you basically collect the terms with dp and dv separately, we will get an equation like this. Now after doing that, just do the integration both side. Okay, so dv by v gives you ln v, and if you do the integration this side also give you 2 ln ap plus 1. Okay, let's take this side, the right hand side, some constant. Let's consider ln c, some constant c. Now if you take the ln as common, so ln will become, so v into ap plus 1 whole square, right? Ln c. And put this 2 into the power of this inside thing, so it will become ap plus 1 whole square, right? So now it will become v into ap plus 1 whole square equal to c. So this would be the equation of state for this process. Okay, for the process that is mentioned into the problem. Okay, so this is the way you have to solve the problem. So for this type of problem, where you have to find the equation of state, so in that case you have to always start from the first law of thermodynamics, and by substituting the necessary condition and necessary expression into that particular expression, you will be getting, after doing some algebra, you will be getting the equation of state for that particular system. Okay. Next is the problem 5. So problem 5. Reversible engine cycle is shown in the following TS diagram. Okay. The efficiency of the engine is given by, that you have to find out actually, given by what? The diagram The TS diagram looks like this. The TS diagram looks like this. So this is the form: 2T1, T1, S1, 2S1, 3S1. Okay. So efficiency, we know the formula is simple. Eta is basically given by W by Q. Okay. W by Q. So W is the work done. So the work done, we know, is the area under the curve. So here the work done would be this for this curve, right? This area. Basically the area inside the cycle, right? A, B, C. So area under A, B, C. So that would be simply half into T1 minus 2T1 minus T1 into 3 3S1 minus S1, right? That would be basically the area under this triangle. So half into T1 into 2S1. Okay, so T1 into S1 W. Now Q heat input, we know is area under this ABC. Okay, this thing, this whole thing. Area under BAC. So area under BAC, curve BAC. Okay, curve BAC. Okay, so that would be basically this whole triangle plus the area of this rectangle, right? So that would be first the area of this triangle, that is T1 into S1 that we have previously calculated, plus area under this rectangle, right? This rectangle, area under this rectangle. Okay. So that would be 2S1 into T1. Okay. So now the efficiency eta would be T1 into S1 divided by T1 into S1 plus 2S1 into T1. So if you do that, it will give you 1 by 3. Okay. So the efficiency is basically 1 by 3 for this side. Now the problem 6, question number 6. If the completion ratio of a diesel engine is 15, and fuel cutoff ratio is 3, then find the efficiency of the engine. Take the gamma as, assume gamma as 1.5. Okay. The options are A 60%, option B is 72%, option C is 64%, option D is 56%. Okay. So we know the formula. It's just putting the values in the formula. Okay. So eta is basically 1 minus, for the case of a diesel engine. Okay. 1 by R to the power gamma minus 1 into rho gamma minus 1 into rho gamma into rho minus 1. Okay. This is the efficiency we know. So here into the problem, everything is mentioned. So R is here, basically the compression ratio, that is R, is 15, and fuel cutoff ratio, that is rho, is 3, and gamma is 1.5. So just substitute all of the values here in the formula. It will be getting 1 by 1 minus 1, 15 to the power 1.5 minus 1 by 3 to the power 1.5 minus 1 by 1.5 into 3 minus 1. Okay, if you do the calculation, you'll be getting as 0.6385. Okay. So around, you can say it's around 64%. Okay. 64% efficient. Okay. This one will be the correct answer. It's easy, just you have to put the numbers into the formula. Okay. Problem 7. In a standard auto engine, the air intake place at 1 atm, okay, pressure, and at 30 degrees centigrade before the ignition, the pressure of the combustion chamber is 16 times the initial pressure. Okay. Find the compression ratio. Find the compression ratio. Given gamma equal to 1.5. Okay. The options are option A 5.65, option B 6.35, option C 8.23, and option D 1.24. So here from the problem you see it's mentioned before the ignition. So before the ignition, we know this compression stroke is basically happening. Okay, so compression strokes means the piston is basically compressing the air. Okay, that's why the pressure got increased. So in this case, the pressure is becoming 16 times from the compared to the initial pressure. Okay. So this process, this compression process, we know this is a adiabatic process. Okay. So the initial and final pressure and volume will be related by this equation, right? So during this compression stroke, it's adiabatic, right? So the relation of pressure and volume will follow this relation, P1 V1 gamma equal to P2 V2 gamma, right? So V1 So P1 by P2, or sorry, P2, that is the P final, by P1 would be V1 by V2 to the power gamma. So P2 by P1, you know, P2 is 16 times P1, right? So it would be 16 into V1 by V2, 1.5. Now using a calculator, you can easily calculate this. V1 by V2 would be 1.5 is basically 3 by 2, right? So if you put it this side, it will become 16 2 by 3, right? 16 2 by 3, if you calculate, it will give you around 6.35. So V1 by V2, that is the compression ratio, R V1 by V2 is equal to 6.35. Okay. This would be the correct answer. Next problem, problem 8. Calculate the efficiency beta of an engine with an ideal gas operating in the cycle shown in this figure. Okay. So gamma equal to 1.4, you have to assume, and the figure looks like this. It's a PV diagram. So PV is so this diagram looks like this. 3P0, P0, V0, 2V0. This is adiabatic process. This whole process looks like this. Okay. Now from here you have to calculate the efficiency of eta. Eta, you know, general formula is eta equal to W by Q. Okay. Okay. So now here, so W is there four, there three ways the work is happening. So let's name this A, B, C. So W is so work done is W from A to B, there is some work. W is B to C, there is some work. W from C to A, there is some work. From A to B, simply the volume is increasing at constant pressure. So P0 into V0 minus 2V0. So initial volume was 2V0, from it becoming V0. So V0 minus 2V0. From BC, there is no work done since the volume remains constant, so it's 0. And for WCA, we know there is this adiabatic. So for any adiabatic process, we know this work done is basically for any adiabatic process. We know the formula is P final, B final minus P initial into V initial by gamma minus rho. This is the formula for any adiabatic process that we have done in the previous classes also. So in this case, it would be 3P0 V0 minus 2 P0 V0 into V0 by gamma minus 1. Okay. So if you do the calculation, you'll get V0 by into 2 minus gamma by gamma minus 1. Okay. Now the heat intake during this process would be this way, the heat input, Q input. So the Q input would be, we know, it's basically CV delta T, right? CV T T at B minus T at T. Now we know from, since it's ideal gas, so we know that from ideal gas relation that at B 3 P0 V0 equal to TB into R. So TB you can write as 3, oh sorry, NR, right? So 3 P0 V0 by NR. Similarly at A you can write TA as P0 V0 by NR. Okay, I guess the problem is mentioned also. Let's consider for one mole of gas. Okay, so let's consider N equal to 1. So CV equal to, so CV into, it will become R by 3 P0 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 minus P0 P0. Now for CV by bar you can write it as 1 by gamma minus 1 into P0 P0. Now from here you can write eta as W by Q. Now if you do substitute it, it will become 1 minus gamma by 2. Substitute value, if you substitute the value of gamma, that is 1.5, you will get this as 0.3. This will be the value of eta. Okay. Okay. So this is simple. So basically you have to calculate the work done for each of the processes, and next you have to calculate the heat input. Okay. So since here this heat input sign is positive, so during this process only there's a heat is getting inputted. Okay. So after calculating all of this, you can easily calculate the efficiency. Okay. So this is our last problem. So if you have any question, you can ask.
I want to confirm one thing, that in the TS diagram, when we
Yes.
want to find Q or W, we have to take area under curve, right? And in
Yeah.
the PV diagram, we have to take the PV, work equal to PV.
You want to calculate work done, right?
Yes, yes.
Yeah, work done you can calculate. In what you can do during each process, you can easily calculate the work done, right? Like here, how we have done. Okay. For each of the processes, you can calculate its corresponding work done. From there, you can calculate the total work done. Okay. By
Yes, but if it
adding the
was
work done for all processes. Okay.
yes, if it was TS graph, then we would have to take
Yeah.
area under curve of the
Yeah. Area
total
under the
curve.
curve. Yeah.
Okay, okay,
Area for a cyclic, it should be a cyclic process. Okay. Area under the whole closed curve. Okay. Yes.
okay.
Yeah. So that's it. So so I will now closing the session now. Okay.
Thank you, sir.
Thank you for your attention. Thank you for your attention. Okay.